We're going to learn today multiple regression using La Quinta-In example. It's a very long example. It has a lot of explanations on what are the variables, what are the units of the variables. So I suggest that you pause the video right now and read through the problem before continuing. Now, as you read, we are looking to predict the operating margin of new hotels given certain variables. And if we open the file, the variables that we are using are to predict the operating margin. Operating margin is going to be my dependent variable. That's the one that depends on many others. My dependent variable is given as percentage. And then we have the number of motel or hotel rooms within 3 miles of the hotel. We have also the number of miles to the closest competitor. We have the office space available in the area given in thousands of square feet. It's really important the units that you use. We have enrollment to be in hundreds of people. Income is represented like the median income in hundreds of dollars, and distance to downtown in miles. So once we start our notation, notice that we put the names of the variables, and also don't forget to put the units. We will see later on how important this is. So we start looking at the data, and there's a big concept here that applies for multiple regression, and that is we want to see if there is a multicollinearity problem within the independent variables. Multicollinearity means that there is a high correlation between independent variables, between x's, and it is measured by the coefficient of correlation. So we assume there is a multicollinearity problem whenever the absolute value of the correlation coefficient R between xi and xj is greater than 0.7. So we first need to get all the possible correlations between the x's. And we also include y just because we're going to use y to check which ones, if we find any problems with multicollinearity, which ones of the x's we're going to delete. And we use the y correlation with those corresponding x's as a criteria to delete the variables. The first step is getting to the first title, going to data, get on data analysis, correlation matrix, and then we're going to select all your data. Go to the first title, Control Shift right and down. That's how we make sure we collect all the data. We select labels, and where do I want my output? So let's assume I just want my output here, and OK. I just like to see this in a clean way, so I usually just put it in center and decrease the number of decimals to 2 decimals. Then I highlight where the y is. Why? Because notice the y is margin. If I highlight this, nothing highlights, so I just highlight where my margin is, and it represents the correlation between y and each of the variables. So this is not going to be part of my multicollinearity test. We never test for multicollinearity in the correlations between y and the x's. We only check for multicollinearity in the correlations among the independent variables x. Now, one important thing is that when you run your correlation matrix, y, or I should say when you run regression in overall, y should be either on the far left or on the far right. But y can never be in between the independent samples, independent variables. If y is inside between two independent variables, we should remove or move the variable to either the far left or the far right. Now the place that it stays, it's going to change your correlation matrix. Let me show you how it looks when the y is on the far right. I'm just going to place it here. Notice that it changes a little bit in terms of margin now is a row. So all you have to do is see where your y is, highlight it no matter if it is a row or a column, just to make sure that you do not analyze those as part of your multicollinearity. Now, analyzing for multicollinearity here, we can check that there is one problem between miles and rooms. So there is a multicollinearity problem here between x1 and x2. Let me add here the names of the variables so that I remember to just say x1 and x2. Now, when I come back to my correlation between each of those x1 and x2 and my y, I see that the highest correlation with y is miles. Therefore, I come here and I say, yes, I found a problem between x1 and x2. The correlation was 0.74. Okay, and the highest correlation with y between those two variables is miles with 0.16. So it's x2 with 0.16 as my correlation. Now what this is telling me is, what do you need to delete? We always delete the lowest correlation with y. In this case, we're going to delete x1. What does delete means? That means that I'm going, let me place this back to where it was so you don't get confused. Delete means that I'm going to go to x1, notice x1 is in B, I'm placing my cursor over B, right click and delete. Now we have only 4 variables remaining and we're ready to run regression. Notice that we're following the regression procedure that's in the book, and it says we first identified my variables. We did that. Do we have only one variable? No, it is multiple regression. Run the correlation matrix. Do we have any problems on multicollinearity greater than 0.7? Yes. Is there a repeating x variable? No. Now we're going to use analyze r between x and y. That's what we did. And delete the lowest r with y. We deleted x1. Now the next step is to run regression. So we go back to our data and click on data, data analysis, regression, and we select my y. So use always the titles, Control Shift down. For the x, I always go back again, click on miles, Control Shift right and down to select the rest of the variables. Make sure you check on labels, and confidence level only refers to a question that's asking for the confidence interval for the population slope of any of the variables in the model. So we briefly go through all the questions in the problem and see if one of those questions is asking to estimate with certain percent of confidence level the population slope for a particular x. Let's look at our questions. First, are there any multicollinearity problems? That's where we were. Is the model valid? Blah blah blah. Go down. Notice 5 says estimate with 94% confidence level the slope for household income. So it is asking for the confidence interval for one population slope. The rest of the problem of the questions, we're going to use alpha of 0.085 unless otherwise specified. But in this particular question, we use 94%. And that is the percentage that we are referring in the regression dialog box. So we need to check 94%. What if you don't have any question that asks for the population slope of any independent variable? Then you just don't use it. Where do I want my output? And finally here, this is done, the residuals and normal probability is to check for very important assumptions in regression. That if you're interested, you can read more about it, but we're not going to cover it in today's example. Now when we look at the output in regression, let's go one by one. The multiple r, we already covered that r is the coefficient of correlation And it can be interpreted as a number from -1 to 1, where 1 is a perfect relationship, 0 is no relationship, 0.5 is moderate, positive or negative, 0.25 is weak, and 0.75 is strong. So that is what multiple R is. Now this is the coefficient of correlation, but it applies for simple regression only. Okay, so make sure that when you have a multiple regression like the example we have here, we don't use that as my coefficient of correlation. Instead, we go and look for the values in my correlation matrix, and each of these are the coefficient of correlation, individual R's, for the relationship between y and each of the x values. The next one is the R squared, and this is the coefficient of determination, and it's for simple regression only. So it's good to memorize that the first two coefficients given in regression are for simple regression only. The next coefficient of determination, which is the adjusted coefficient, is done for multiple regression. In this case, we have a multiple regression, so we're going to use this coefficient. Why? Because it adjusts for the number of independent variables that we have in the model. The regular coefficient does increase as we add variables, independent variables. So as we keep adding x1, x2, x3, x4, x5, it doesn't really look at how the relationship is, but it just increases huge when you just keep adding variables. Whereas the adjusted coefficient is more conservative. So we're going to use that one for multiple regression. Standard error, we're going to check on this concept later on, but the standard error is represented by SE, and you want to make sure that in any formulas that we use later on, if it says SE, you know where to come and look for the standard error. Now, so that we understand a little bit, the standard error of the whole regression is really the standard deviation of the error term. Okay, so we use this to estimate sigma, and that's an important concept. So we use the standard error to estimate sigma. Now, the next one is the sample size, which is n, and then it gives us the ANOVA table. So let's go back to our questions and see what is next after checking for multicollinearity. We need to see if the model is valid. Remember that the model here is going to have an equation of beta 1 equals, of y hat equals b1 plus b2, and each of the times we multiply by the x. So at the end, you are going to have a regression model based on betas. Now, what happens if all these betas are equal to 0? Then you're going to have just a number, the intercept is just a number. Then we're going to have 0 times x1 plus 0 times x2 plus 0 times x3, and there's not going to be any model. So it's important to verify before we start checking on regression that the betas are not equal to 0. And since we're testing many at once, we use ANOVA. So we go back to our data and notice that the ANOVA table is already given to us. Significance S is my p-value, F is my test statistic, and then we have the everything else similar to what we had in the ANOVA chapter. A good practice to go back to ANOVA would be, well, what if I just give you 2 of the sum of squares and I give you the equation? Would you be able to fill out the ANOVA table? And that's part of the material for multiple regression, and that is covered in the book. So don't forget to go in the book and check what would be in a case that I have a blank ANOVA table would I be able to fill it out? It's the same as ANOVA. The only thing that might be a little confusing is that when you add the number of variables in the model, you have to add the dependent variable. So in our case, how many variables do we have? We have, let me go back. We have 1, 2, 3, 4, 5 x variables plus 1 that is my y. So remember that the first degrees of freedom is number of variables minus 1, k minus 1. We have 6 variables. 1 of them is dependent, 5 of them are independent. Minus 1 is 5. So that's the big thing. But the rest is the same. And I want you to also see what is the relationship between the mean squares for the residuals, MSE, and the error. The standard error is computed by the square root of MSE. So notice I got to the same value, but I just get square root of MSE. That's really important for you to know too. As it is important to know that the R square, remember the R square, the coefficient of determination? The way I get my R square is going to be by doing the sum of squares for the regression SSTR divided by the sum of squares of the total. Why? Because really, if you think about what the coefficient of determination gives us, is the percentage of variation in the model, in the y, that can be explained by the model, by the regression model. And the total variation in the model is SSTR divided, the total variation based on the model is SSTR divided by the total variation. That's going to give me the percentage. So it's good to know that once we obtain the average of the R squared, then you will be able to get your R, because R squared, R is just the square root of R. So notice how we can get values from the ANOVA table that in case they give us this blank, we will be able to compute. And finally, the last one that we could compute also is the adjusted R squared. The adjusted R squared, there's a formula in the book there for this. It's displayed in the screen. And we're going to follow this formula now that we know what k is. K is the number of variables. We have, well, how many? We have 5 independent plus 1 dependent. We have 6 variables. We have 100 sample. R squared, we just computed that. So if we follow the formula that I just put on the screen, it will be 1 minus the R squared times n minus 1. Let me just put n minus 1 divided by n minus k, 6. We do that and we obtain 0.1370. So again, notice how we can compute all these. You have to go back to your ANOVA on how to compute an ANOVA table if I just give you 2 of the sum of squares. But let's keep working. We're going to see if the model is valid. So we need the ANOVA results. We need this p-value, we need this test statistic to create our ANOVA. When we use the template to fill out the ANOVA test, notice that we're testing that all the betas are equal to 0 or at least one differs from 0. We're using the p-value, so we need to use the test statistic in my diagram. And we're going to reject the show if the p-value is less than or equal to 0.085. We get from Excel that my value is, my test statistic is 9.55 and my p-value is 0. 2.14 e minus 7 is 0. And therefore we reject the show at alpha level and we say the model is valid. Notice that every time we reject, the only interpretation is the model is valid. When we fail to reject, then we just say the model is not valid and you stop here. You cannot do anything else, because what it means is that all your independent variables are not good to predict your dependent variable y. So that being said, we have a model that is valid, so we continue. And then looking at my questions, it says we tested the model is valid. Now, should all the variables be included in the model? Testing that the model is valid, it only tells me that at least one of them is not equal to 0. But what if only one of them is not equal to 0? Then we need to go and find which one is not equal to 0 and keep that in my model and delete the rest. So we want to delete any variables where the beta equals 0. And for that, we do individual t-tests. For the individual t-test, my hypotheses are going to be individually written. Like if I'm performing 5 different hypothesis tests where I test that each of the betas equals 0 and each of the betas is not equal to 0. So it's basically we're doing 5 different tests here. And that's why I just ask you to do a general diagram where you know we're using the p-value approach. So we're selecting this as my p-value. And we know we have a negative test statistic and a positive test statistic. If we really wanted those values, then we go to the last table of regression. And let me just simplify this to 4 decimals. I just select everything and go and decrease the decimals to 4 just to make it look clean. Then the first line for the intercept, the only information I need is the coefficient. So I always delete it just to make sure I don't get confused. And then I have the t-test statistic and the p-value for each of the betas, for each of the remaining variables. So if we really wanted to do diagrams with each of the test statistics, here they are. But we're just going to use the p-values and copy them into our template. Now notice that I do not use x1 because we already deleted x1. And then we use briefly the decision rule in each of the cases. Reject HO if p-value is less than 0.085. Is this less than 0.085? Yes, so we reject. Is 0 less than 0.085? Yes. 0.877 less than 0.085? No. 0.02 less than 0.08? Yes. 0.14 less than 0.08? No. And then we apply. Notice that rejecting. What is rejecting? Why is this good or bad? Rejecting means that I'm gonna know that the beta is not equal to 0, which is basically what we're looking for. We want the beta not equal to 0. And therefore, if we reject, we're gonna keep the variable in the model. We're not gonna delete the variable. Every time we say yes, we're not gonna delete the variable. Now, if we fail to reject, what we're saying is, in the case of 4, we're saying we're failing to reject HO. So we're assuming that this is correct, which means that the beta equals 0. If I go back to my equation, then it would be like saying 0x4. And that doesn't make sense, so we're going to delete that variable from the model. And therefore, your conclusion here is we're going to delete x4 and x5 from my model. So I go back to my data, my original data, and I look into x4 and x6. x4 is enrollment, so I place my cursor over the D and right click on that, delete, and then I go and right click on distance and delete. So now we only have 3 variables. Please do not make the mistake to just use these coefficients and just keep enrollment and distance, because those are the variables that we deleted. But remember that everything else, all the coefficients are done using those 2 variables too. So we cannot really use the same model that we used before. So once we say, should all the variables be included in the model, notice that my regression procedure says, we run regression. Is the ANOVA valid? We said yes. Do we have simple regression? No. Did we analyze individual t-test? Yes. And we deleted the corresponding variables. And now it says run regression. So if you delete variables, notice that the procedure is telling you all the time, whenever you delete anything, you have to run regression again before you get to your regression equation. So by running regression again means that we're going to go to my original data, go back to the top, go into data, data analysis, click on regression, and the only change basically is the input x because now we don't have 5, we have only 3, so we go to miles, Control Shift right and down, and then my output range, we just keep it on below my previous output, and we click OK. We don't have to do any more of the previous tasks. The next question in my problem says to give you what is the regression equation. So we work with my regression equation based on the coefficients in my output. The coefficients, and let's use 4 decimals in case you're going to use the calculator, but the coefficients, this part of the table is going to give you the equation, and notice how that translates into my template. Notice that the intercept, and then we have each of the other coefficients, which are the slopes for the remaining variables that we have. Do not confuse to use 1, 2, and 3. Use only the remaining variables that we have in the model. Now that we have completed the regression model, then the rest of the material is very similar to the simple regression example. I will split the video and I will continue the video later on for questions 5 and on.